This workshop is more about data than theory. So the real the crux of the things will start beginning from now in the tutorials. And the lectures are supposed to be supporting the tutorials to help you understand. You get some background before you actually get into the data. So something to keep in mind is that there are many aspects of general data analysis, of gravitational waves, of the instrumentation which goes behind the detectors, which give you the data, and many other things, including the scientific outcome and stuff. You don't necessarily have to understand all of them in order to do data analysis. And even within data analysis, there may be certain aspects of the programming language that you don't exactly understand. So there are many unknowns. And if you strive to understand all of them before even starting to work, you will not be able to get anywhere. So what we do is like black boxing things. We say that there is some black box. Let's say the detector is a black box. I don't understand how it works, but someone has told me that it gives this strain, which is a time series sampled at whatever rate. And these are the assumptions which went behind giving you this time series. All you need to know about the detector is these two things. And then you can do some processing on it and give it to someone else. All they need to know is the final result of your processing and the assumptions behind that result. They don't necessarily need to know what you did, what processing you did. So this is like you black box the detector and someone else black boxed what you did, but the science progresses, work still happens. So that's the idea now. I'm going to not assume anything about whether you know any instrumentation before, or whether you know GR, or whether you know gravitational waves. And most of the workshop you can understand without having to understand each of those things. So for some starting motivation, you were shown this plot, I think, in the first lecture. So this is showing which detectors were on at different times. And if you just sum up these on-time durations, it's about 40 months of detector strain data. For 40 months on the clock, not continuously, at least one detector was on and was collecting some strain which could contain a GW in it. So if you convert that 40 months, it comes out to be around 10⁸ seconds, just 40 into 30 into 24 hours into 3600 seconds per hour. So that's about 10⁸ seconds. Now, if you go to this public website, which shows you the latest alerts, there are about 250 signals detected in O4, overall some 300 signals, of the order of 300 signals. Now, each gravitational wave signal is roughly a second long. So that's about 300-ish seconds of real stuff in 10⁸ seconds of nothing. So that's like a 1 in a million search problem, which is, I did some Googling. It's like finding a needle in this bigger haystack. So let's stretch this analogy a little bit further and understand what we mean by doing this gravitational wave data analysis by looking at how you would search for a needle in a haystack, literally. So first thing you need is data. I mean, LIGO has collected it, but how do we get data? That's the first thing. How do we ourselves get the data so that we can start working on it? And also, how do we handle it? So in the case of the haystack and needle, maybe you could have an Amazon delivery. I don't know how do you get it. Maybe go to a farm. And the way we handle it there is through our hands. So in the tutorials, we will teach you how to download the data, either programmatically. Ritesh has already showed you the websites where you can go click, 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 click. It will give you a link. You click download and it will come to your data, come to your computer. But there are also programmatic ways of doing it, which is what we will do in the first tutes after this is done. And so the next thing you would need to understand so that you can do data analysis is to know what you are looking for. So you need to understand what the signal looks like. And if you, for example, if you thought that needles are spherical balls, then you are not going to find them in the haystack, right? You have to know what you are looking for. You have to have a correct model. So which is really, what is the thing I'm looking for, which is the needle, and what it is not. Both are equally important. So in this case, needles are long compared to their thickness. So they are long, thin, and pointy. They usually sink in water. They usually don't burn, and they are usually magnetic. However, if you have a wooden needle or a plastic needle or maybe a bone needle from old times, some of these things will not hold, and they will need some different methods than what you could think of. And something else to keep there, they are tough and sharp objects. The other thing you need to know is what you don't want, which is the noise model, or in this case, it is the hay. So again, the same question, what it is and what it is not. It is also long and thin, which is why it's a very pesky noise source, because it is similar to the things we are looking for. And it is also pointy, but some things which it is usually not is that it floats on water, unlike needles. And it usually burns, and it is usually non-magnetic unless it is contaminated by, let's say, iron-rich soil. And it is weak, unlike needles. So you need to understand both of these things so that now you could say, oh, given this haystack, I can start rejecting noise. And if I find something which looks like signal, I will keep it. And then you do this for the whole stack. So there is some ultimate test that you do, which tells whether a given thing is actually a needle or a hay. So in this case, it would be, what you are trying to know is some ultimate test, which is like the best possible, theoretically best possible thing you could do to tell whether something is a needle or a haystack. In this case, it would be my grandmother. I would give her some object. I will ask her, is this a straw or a needle? And she will tell me exactly what it is. Just an example. The issue with this is that for every object, she is going to need some time to look at it and tell me what it is. And if you do it for the entire hay, which is like 1 million objects, it's going to take months to do this, And it gets worse for gravitational waves. It turns out that this ultimate test, which is called Bayesian inference, it takes about 100 hours per little chunk of data. Now, 100 hours times all those 10 raised to 8 seconds, I'm not going to live that long. So how do we do this in real time? So what we need to do is some sort of a pre-selection, which is the technical term for this is search. So we search for things which is really just cheaply removing, without doing this ultimate processing, we just cheaply remove as much noise as we can while keeping as much signal as we can. And some examples in, where does this keep happening? So here it would be like, you could take that haystack and you could burn it. You will be left with some ash, which is much less volume to go through. And then you could apply some other methods like just search for things. Or you could put it in water, needles, and some contaminated hay will sink, and you just have to look into that little part. Or you could scan it by a magnet. Now, it depends on what kind of signals you are looking for, what process, what pre-selection you use. For example, a wooden needle will probably not show up in any of these, and it would be really challenging to cook up some initial search algorithm which will remove most of the noise. Okay, is the philosophy clear? There are these 5 big blocks that you need to understand, and their purpose is this. How do we get the data? How do we understand the signal model? How do we get the noise model? And a pre-selection, and a final Bayesian inference. Everything all right so far? Any more questions? Okay, now something else I need to show before we get into actual coding is how advanced Python programs usually work. Are all of you familiar with this type of coding? You know this, right? You define some global variables and you can use print statements and write some functions which take some parameters and return some values after doing some processing. And then you can use those functions later on. So while this is fine, this often becomes a huge problem later on as you have bigger and bigger codes. If you just keep listing all these functions which have different inputs and stuff. So something which people do is related functions are grouped together into something called a class. So in this case, the example I'm giving is just gravity, Newtonian gravity. So it has two functions which are sort of related. There is a field which depends on some location r prime at which you are evaluating it. And it depends on the mass of the point which is creating the field and the position of the point. Okay. So what we do is we build a class to group these two things together. So the field is created by mass and its position, and it depends on how far you are from that mass. And so what we can do is, since the same mass is going to give rise to a field and a potential, you can create a class called a point mass, which has these properties called the mass and the position. And you could also, since in the end all you use is this GM in both the places, you can also define a strength right in the beginning so that you don't have to recalculate again and again. And then these two functions are a part of that class. They are attributes of this point mass. And for these functions, you don't need to give the mass and position again and again. You just give the r prime where you are trying to evaluate this. And then it returns the thing. Now, it still keeps fluctuating a bit. So, and then so here you would just use the function as it is. It's called def field. So you just call field with whatever parameters it had. Here you have to first create an object of this class, which is called this. So A is the name of the object, some variable name, which is an object of the point mass class initialized with these two parameters, which are the mass and the position. Have people seen this kind of thing before? Is this new to anyone? You can spend a bit more time. Okay. And the way you access the things which belong to this object is through a.m. So a.m is A was a point mass class with these two parameters. So a.m would be whatever m you pass, which would be 3 here. And a dot field at r would be, again, this function evaluated at r. Now, the next order thing to this is you put this in so this would be the script you are running, right? Use a Python, whatever this file's name is, .py. But you could offload it. You could offload just this part into a different script called gravity.py, which just contains the whatever global variables that file needs and the class which does the calculations. And then in your actual run script, you import that script as import gravity. So whatever this name was, you just drop the .py and just import it. And then here you can call things which were defined there, like G was defined in gravity.py, you call it as gravity.g, or the class which was defined as gravity.pointMass something, and then use it like this. Okay? So now let's begin with the tutorials. GWODW, GitHub. So go to this, open tutorials, accessing open data, discovering open data. So I'm going to use Google Colab. Please show us your status of this very first step of opening the tutes. Okay. So let's start with this. So first we need to install some things, which is sort of like you are trying to download the code that someone else has written, all these functions, onto the whatever local thing is, so that you can import it like this. So the codes we are trying to install here is basically this one called GW Open Science Center. This was a website which Ritesh showed you. This one, gwasc.org. So here, if you go to software and libraries, this has it's a Python package which you can use like this. So just the way here in this gravity, I had this class called point mass, and then I could use it as gravity.pointmass. Here, this GWASC has a class called datasets, and it has these functions: dataset type, event at GPS, event at detectors, and stuff. So these are some. So what we are going to show in the tutorials are some examples of these functions, but there are more. If you want some specific kind of data which you are not able to access easily with some of the functions you have already been shown, here is where you come and see if a function already exists to do the kind of things you want. Oopsie. So let's begin with first installing this. Just uncomment this line. If is anyone running on their local system? Can you show, please? Everyone is running. You are running on. Okay, fine. Everyone is running on Colab. Yeah, Colab, right? Okay. So uncomment this line and run that cell. Yeah, ignore the warning and go on. Okay, there is a step you need to do. After this, you just say restart session. In runtime, restart session. It's just something you have to do. And then run the same cell again. Good. And now you import it and check the version working. Everyone able to get to this point? Without this, we can't progress. So let us know. Okay. Okay. Help. You need help? Explain. Okay. What do you need me to explain? Oh, help. Okay. You need to keep the exclamation mark at the beginning. Yeah, let me. So, you guys have used terminals before? You know, this kind of thing where you say, ls, for example. Have you guys done this side of things? So, if you want to use a terminal, wow. Okay, I'm sorry about that. Okay. If you want to use a terminal from Python, a Jupyter notebook, what you do is you come here and in the cell, you use this syntax. So this exclamation mark is like telling Python to open a terminal. And okay, something you may want to know is how do you quickly uncomment and comment? So control and slash, forwards this. So this, if you do control plus slash, it will put a hash or remove it from the beginning of the line. So just like that. Okay, are we good to go? I don't think I am. Okay, so first we are going to use GWASC, this website, except instead of now clicking through things like get data, events and catalogs, and then events, and then click on some event, and then it will give you these links where you can go. Oh shit. Okay. And if you click on it, it will download the data for that event. Instead of doing it in this way, you click on a website, we are going to use Python programs to understand and do this simply. So first, before actually going to the data, we need to understand what data sets are available. So for that, we are going to use these classes, which are gwas.datasets, which has function called find dataset. And if you just run it, it will list all the available catalogs and their type also. So there is a GWTC. This means gravitational wave transient catalog. And then there are different catalogs available. So there is a GWTC1 confident, which is, sorry, Zoom. Oh, okay. Yeah, better. So there is a GWTC1 confident, which is a catalog of all confident detections in the first release of the gravitational wave transient catalog. And there are also marginal candidates, which we are not entirely sure about whether they are noise or real signals. And then subsequent releases have these things. There are also some from auxiliary. There is also a catalog which contains events which were detected by collaboration other than LIGO. So LIGO has their data, but once they release it, anyone can search through it. And there is this group which does this independently. There are also results from the initial LIGO-Virgo. In case you want data from there to maybe you find some signal, you have a signal model which may be detectable even with a less sensitive version of LIGO. You could search through that and some other things. Sometimes LIGO releases part of the data before the entire catalog is released. So that is like, if LIGO finds something super interesting, like this BNS signal in 2017, this simultaneous gravitational wave and binary neutron star merger, which was seen in the sky. So the data for that event was released shortly after the paper was published. But the data for the entire run was published a year later. So these are called discovery papers of sort, and then their data is just released slightly earlier. That also you can access. So, right. Next, in a given catalog, you could list out what all events were detected confidently by LIGO. So you use this function datasets.find datasets. This time you want events. Earlier it was catalogs. And in the events, you say which events you want, they are from this catalog. These names you take from one of these. So for example, if I put ISO3A, so they are not GWTC1 events. I should have changed that. So then these were events detected by in that catalog. Is this fine so far? Anybody needs, okay. Anybody needs help? No, all good? A quick show of hands. Okay, good. Let's move on. So now, so we found which catalogs there are and what events are there in those catalogs. Now we want to see what all big actual strain data sets there are. So these were just some names of events which were detected, but now we want the actual strain, the detector strain, which was recorded during that. So for that, we first need to find out what all runs are available for which we can query data sets. So this time you again use the same function, but the type is now called run. So these were all the runs. These S5, S6 are the two runs just before we actually detected an event. So LIGO has been building and developing their instrument for a long time now, but it was only after 2015 or 16 that it became famous. But it was also operation before that. These were some runs at those times. And then these are again those pre-releases I talked about just for these special events which were detected. And then there are also some full O4A, O4B, these kind of things. So all these are just these. Yeah. So these, all these runs are what these are. So now that we know what to find, we are now going to find some, what kind of events can we find in a given time window. So there are different kinds of things, right? You may want to search for strain data based on the event name. Maybe you think that this 170817, which was a binary neutron star merger, you have some scientific theory which says that a binary neutron star merger should have this additional feature in the strain data. So you may want to targetedly just find that strain data by the event name. Or you may think that there was some other phenomenon which occurred somewhere, some supernova went off, and you think that there should be a signal during that time window of that supernova. So then you would want to search for data based on a time window. So these are these time windows. These numbers, these are some 9-digit numbers you can see. So these are GPS seconds. So there is a clock which is counting time from some reference time which was chosen somewhere. You don't have to worry about it. There exist functions which transform to and fro that date to whatever time stamp you are looking for. So if you want to find out the GPS time corresponding to, let's say, now, you think that a supernova went out now, then you would go to that whatever website it is, put in your current date, and it will give you this number, and you can come back and put it here to find out the exact timestamps. And then you look for, you also can further specify what kind of things you are looking for. So within this time window, just give me actual events which were detected in this catalog by this instrument. So L1 stands for the Livingston instrument, H1 is the Hanford instrument, and V1 is the Virgo instrument. So that's it. You could also do the reverse. If you don't know the actual GPS time for some event, you could just give its name, and there are functions which give you that GPS time. And its inverse, which is you give time and it returns the GPS, sort of like a targeted version of this thingy. And yeah, something to note, if you just say, oh, I want to have fun, and just put some random numbers here. So there is no event within that random time, and you will get an error. So in some sense, like this is, you have to know what you are looking for in order to use this function. But there are other ways of finding data anyway. And if you don't know exactly what the starting and end GPS times are, you can find those also. So these are the actual GPS times which correspond to the start and end times. Or the opposite also, if you just say what run was going on at some time, you can find that. And yeah, some more filtering. Now how to get actual data files. So here, can someone tell me the, right, I have half an hour more. Yeah, good. Yeah. So now how do you get actual data? So these, I showed you this one way, right? You click, get to this point for that event, and then you click on this file, and it will give you some 4,000 seconds of data sampled at some sampling rate. But the computerized way of doing that would be to use this guas.locate get event URL. So URL is really a link. So example, this up here, whatever is in that bar, is the URL. People know this basic web surfing stuff. So this is called a URL, and a download link really. So when you go and click here, it's actually a URL. Down here you can see there is a link. So that is a URL, and when you click on it, your browser goes there and downloads whatever is at that URL. So programmatically, all you need is some way to give that it's like a string of characters. So that function is this, getting event URLs. So for instance, let's actually work for this example only. So I'm expecting to get some error. Let's see. Oh, it works. So it has given this link, some stuff. It's an O4B2 discovery paper. And now let's see. This is the same string as what that function returned, except you didn't have to visually click. So this may be easy if you are just working for one event or something, but if you want to do this for many events, then you would write a for loop, which will basically get these for that event list. And then you can either control click or use some command like, and just this. So this is a Linux command which you put on the terminal. So here you would put wget and that link, that kind of thing. So I'm not going to download it here, but I just wanted to tell you how you would actually do this. So yeah, you could also look for some very specific duration around that by a specific instrument, because these are multiple links, all possible data chunks which contain some part of that event stream. But you could look for some more specific stuff, and then that would be maybe just one link. Here is what these different instruments keys are, you need to know. So if you want it for, let's say, KAGRA, the Japanese detector, then you would put K here, if it was observing, that is. If it was not observing, you may get an error. I'm not entirely sure. Yeah, you get nothing. Okay, and so all of this was either by name or by timestamps or by runs and catalogs and whatever has been done. But you could also look for more specific things. I only want to look at loud events, for example, or maybe between some loudness. Then you could search for this kind of thing. So do people understand some intuitive notion of signal to noise ratio? So what you have in a detector is you would ideally want a signal, but there is some noise on top of it. And this noise is additive. Okay, it's actually a bit like that. Okay. Now, if this noise, I drew it, right? It has some scale. It fluctuates within some scale. So that is like its noise variation. And then the signal has some power in it. It's not exactly this, but for now, just take it like this. It's almost this loud, right? So here, the signal to noise is this divided by this. Very roughly. This is not the correct way. People will actually define it properly later. So here you can see that the signal to noise is large. And so you can actually see this gravitational wave over the noise. However, if the noise was fluctuating at this scale, then the signal to noise ratio would be low and you won't be able to find it. So you could, then louder signals would be large SNR and you could look for them. Just specifically, I want only the list of loud signals. So you could use this query events with a selection cut based on that thing you want. So that is some list. You could also look for, let's say, mass 1. I'm not sure if this will work. So this is going to look for most, I hope so, mass, all the events whose, so it's a binary, right? So there are two masses. So the first mass, the primary mass, the heavier one, is between 25 to 30. Let's see if it works. It doesn't work because the key is slightly different. No. So this is a list of all events which have this mass. Something you could use if you have a science case of that form. And now there are some quiz questions. Is everything clear so far? Would people like me to go through something again or just a final show of cards? Final show of cards, anybody? Is everything fine? Okay, then can you answer these questions? Write a piece of code to find out the answers to this. These are rather easy. You just have to go up there, find out some place which was doing that, and then put it there, modify it slightly, and get the answer. If you are doing this course on Thinkific and planning on getting a certificate at the end, you will have to post all these answers there. I will not be giving you enough time to finish everything now here, but later, maybe when you go back home today or after the workshop, you will have to post all these answers there if you want a certificate. Okay, let's just do one and then we will move on. I'll pick the easy one, which is asking how many months did O2 last. So how would you do this? You need to, yes. So for now, you can either do it that way, like Google how to convert GPS times to dates and then subtract the dates. But for now, a rough answer is enough. So a GPS time is really seconds. Those integers are seconds. You can subtract them, divide by 30, 24, and 3600. I'm going to do that just now. So yeah, up here, I showed you how to get the start and end times, right? So that's what we really need. Except here we want it for O2 and this. And then what we want is to print it in terms of months. So n minus start. So these are seconds. So we divide it first by 3600 to get hours, then by 24 to get days, and then by 30 to get months. So that's about 9 months. And if we go here, where was the plan? That looks about 9 months. Okay. So let's move on. You can answer the rest of the questions later on your own time. For now, let's look at another way of getting data, which may be easier to work with. So this is, do I go back? So in the first tute, we went through this GWOSC, GWOSC. Now we are going to use something else, which was more targeted towards directly just getting into the analysis and starting to work with it using Python. So in the introductory slides, I said that the way you handle the hay and the needle and the haystack is with your hands. Here you do it with NumPy arrays or some NumPy arrays on steroids, which are called GWPy time series objects. So again, let's zoom in. Ui, ui, ui. Kya hua? Okay. Can people open this notebook in Google Colab and again do the first steps of installation and check whether they work? Okay. So please get to this point and let us know if you need any help. Okay. So show of cards. Anybody reach this point? Okay. I think most people are done. So let's move on. There is a note on object-oriented programming. This is basically what I showed you with the classes and the file structure. So here, there I had this gravity.py with a point mass class. Here, the class we'll mostly be working with is called a time series object. There is also a frequency series, but anyway, before getting to it, so we are going to now work on actual strain data. We'll like get a NumPy array of this h as a function of t, which you could plot, make a spectrogram or Q transform, whatnot, or even convert it to sound and listen to it. So first we need to find out the GPS types. So the thing that you work with in GW astronomy or any time domain analysis is the GPS time, because that is the most precisely kept clock with the detector. So first you need to find the GPS times. Again, we will use the same things we learned in the previous tute, which was the GWOSC datasets, event GPS. So let's focus on this event. Its GPS time is given here. And now around this GPS time, let's pick a segment size. So a segment is just some duration during which we will take the strain data. So we are taking a 10-second segment, which is centered on the GPS time. So that defines the start and end times. And now we can query the full data. So here you don't even have to get that URL, put wget, click on it or whatnot. This will directly fetch the open data for you. for a given segment, for a given detector. Here we are going to download Livingston data from a segment which is this. This star segment is really just a way to expand this into a start and end. You could just equivalently do start end, that will work. And verbose is just, it just prints what is going on. So if you run that, so this is literally downloading the stream data from the website. Apparently not. What? Yeah. And then that will not work. Where is the star? Fine. Good. So it fetched one URL. Whatever we were doing last time, it did it internally, and then it read the data, and then this is the time series it has returned. So that's it's there. Now you can just plot it. So it already has an inbuilt plotting function. Pretty slow. There. Have people reached this point? Does anyone need help? Or should I explain anything again? Huh? Matplotlib. Python version. Oh, Python version. I don't know whatever it is. Python version कैसे print करते हैं? We'll take it. Python, but I don't think this will work.
Exclamation mark.
Oh, okay, fine. That is doable. Right. No, there is no such. Is that important? Is anyone stuck become? वो सिस्टम पे कर रहा है इसलिए. ICBC should be doable in 10 minutes, unless
people have done this.
Okay. So show of cards. Do people have this plot or something like this? Good. So what you have just done is downloaded actual LIGO data, and it is now here with you. You can, I mean, there is this internal plot function. You could also do it yourself. So now this was with this GWPy, which downloads open data. In upcoming tutorials, we will be using this kind of fetched open data in terms of a time series to do some further processing, understand what the noise looks like, and measure its properties. Right? That was one of the blocks you were supposed to understand. What is noise and what it is not. So we are just laying down prerequisites. So next, let's use another package, yet another package for doing the same task. But it will be useful. It's called PyCBC. Something to note, CBC is a jargon we use for compact binary coalescence. So this is a very specific type of GW source, but currently the only one we have observed. Compact is two compact objects, they are in a binary, and the coalescence, that's the kind of signal this package aims to analyze.